understood about how to use Biot-Savart law, I want to spend the next 25 minutes to talk about magnetic dipole. Well, if you still remember, I spent a lot of effort in multiple times, right, to explain and introduce and discuss electric dipoles. Now we're in the area of magnetism. Can we also formulate or just to define some equivalent thing as magnetic dipole as our basic field generating device? Okay? So once we define what is a magnetic dipole, we are going to find out the resulting magnetic potential and the flux density of a given magnetic dipole. And in the end, we want to compare the field structure between electric and magnetic dipoles, right? So I'm not going to spend any more time. I'm just going to tell you, this is exactly the example we just finished. A magnetic dipole is nothing more than a circular loop with current I. Okay? Exactly the same problem we just solved. If we have a circular loop with a constant current, this loop has an area of S, right? So this area S and I somehow should give you a well-defined magnetic dipole moment. So we define the magnetic dipole moment. It is a vector, okay? It is a vector. The direction is the direction of the surface normal, right? The magnitude is the current multiplied by the surface area. Of course, you might be wondering, well, if I only have a surface, I might have two surface normals, one going up, one going down. So how to determine the right direction? Again, you use your right hand rule. Your forefingers should follow the direction of the current. Okay, so in this case, the current is flowing in the counterclockwise direction, and therefore my thumb points in the right direction to represent my magnetic dipole direction. Okay? So everything is still using the right hand rule. The forefingers denote the current direction. Right? So in this case, since the current is flowing in a counterclockwise direction, making my magnetic dipole direction pointing upwards. Okay? Since, in this case, well, it's circular, so I know how to express my S, the surface area, is pi b squared. Okay? So magnetic dipole is also a vector. Its direction is determined by your current direction, and the quantity is defined by the current it conducts and the surface area. Now we have complete information. Okay? Let's try to find out the vector magnetic potential of a magnetic dipole. Again, what we're interested is when our observation point is very far away from this dipole. Okay? Which means this R or this R1 magnitude is very big as compared to the radius of the dipole. So this equation is now going to be used because this is something we worked, right? The solution of 3 scalar Poisson's equations, and we combine them together. So once we know the current distribution, we can directly find the vector magnetic potential A. So all I have to do is, well, I have a well-defined differential length for each piece of segment on the dipole. And for each piece of segment, I need to correctly formulate its distance. Okay. So let's come back to this figure. Here, the textbook is trying to, well, first formulate or to find the potential at a particular point. This is in spherical coordinate. This is capitalized R means the radius, theta is your inclination angle, and at this particular observation point, I am having a phi of pi over 2. So I'm exactly on the y-axis, 90 degrees y-axis. Okay? So this R is the distance from my observation point to the origin. But here, what I need is R1. R1 is the distance from my observation point to the differential segment I'm trying to investigate. Right? So somehow I have to formulate this R1 in terms of R, the distance to the origin and the radius. But basically, R, R1, and B forms a triangle. So we know how to proceed. We have the adequate mathematical tool. First thing first, how do you properly express differential length vector? Well, its magnitude must be defined by B defined. Right? Its magnitude must be defined as B defined prime because again, you have an arc. And somehow, because in this coordinate system, even though we're using spherical coordinate system, but we have plotted the x, y, z coordinate. So the first thing is, again, before you proceed, we want to develop the capability to forecast, are there some components that would vanish, that will be canceled out? Okay? So let us decompose A phi into x and y coordinate system. Ideally, dl prime is b defined in the A phi direction, which is correct, but that is not giving you physical insights. So let's decompose A phi into ax and y. So A phi is decomposed into the negative ax direction with a magnitude of sine phi prime, and the y component with magnitude of cosine phi prime. Okay, so this is the moment where you have to think, well, do I want to put everything into my closed loop integration? Which means for each differential segment, it actually contributes to two components. One in the negative x direction. This is x, right? So negative x is actually into the paper. It also contributes a y component. Do I want to include both contributions into my integration? This is a decisive point. Okay, let's try to plot out a circle. Okay, I'm trying to draw a circle, the cross section of my loop. If I'm trying to evaluate this piece of segment, then I can draw the dl prime, and then I can decompose it into the y component and x component. Okay? My observation point is somewhere here, right? Somewhere here. So symmetry tells me I can find another piece of segment here, right? Which is equally distanced to my observation point. What I'm saying is, since the observation point is to the right, so basically this segment and this segment would be somewhat equal. And this one will be somewhat equal. Okay? So for this piece of differential segment, I can find its counterpart here. They all have the same R1 value. Now if I plot this dl prime, then something you notice. This is exactly how I decomposed each dl prime in the phi direction, but as phi changes, x and y component also follows the change of phi prime. But if you analyze only the green part is adding up. But the yellow, for this one, the yellow part is pointing to the right, but for the top it's pointing to the left. So they actually cancel out. Okay? So this is y, this is x. Okay? In the current geometry, x and y is defined in this way. So basically, only the green part is adding up. You don't have to calculate this contribution. It saves your time. Okay. So we plot that remaining contribution into calculation. Okay. Now be careful. We want to perform a closed loop integration. So therefore, I have to start from this point where phi prime is 0 and going all the way to 2 pi. Right? Ideally, phi prime from 0 to 2 pi means a closed loop. But as I stated, due to symmetry, this part is probably identical to this part. And this part is also identical to this part because eventually some terms would vanish. Okay? So in this case, I don't really have to integrate from 0 to 2 pi. I can only integrate from negative 2 pi over 2 to pi over 2. Means I only need to integrate from this part, this point, to this point, and multiply everything by 2. Okay? So I multiply by 2, so now in the denominator I have 2 pi. Initially I have 4 pi. By multiplying by 2, my integrants, the lower part, is now negative pi over 2. The upper part is pi over 2. So eventually I only have to integrate over a phi of pi instead of 2 pi. Okay? So this is my prior knowledge to this problem. They are somehow symmetric. Okay. Another piece of stuff I changed is negative ax direction is now converted into a phi direction. Why? Because my observation point is at a phi value of pi divided by 2. So at this case, at this particular position, a phi is exactly negative AX direction. Well, remember, I'm working everything in spherical coordinate. So I would only expect to see r, theta, and phi. I don't really expect to have AX. That's Cartesian coordinate. So in this particular case, negative AX for this observation point is A phi. Okay, so I have A phi. So now the problem is, well, we took care of the numerator. What about denominator? Well, R1 needs some time, okay? But as I said, R1, and B forms a triangle. And if we assume this three-dimensional angle between R and B is called psi, capitalized psi. Now using the law of cosine, we know that R1 squared is R squared plus B squared minus the multiplication of R and B, and multiply by cosine, sine. Of course, you have a factor of 2. This is something we learned from high school, right? Cosine rule. And now we can use this fact to find the proper expression for R1. So this is purely math. All we're trying to find is, well, RB cosine phi, cosine psi. R and B is now having a three-dimensional angle. But if you remember, what is RB cosine psi? Whenever you have RB cosine, two magnitudes multiplied by cosine, which means you are actually performing the dot product of the two vectors. Okay? You are trying to perform this R vector making a dot product to this B vector. Even though the psi is difficult to find, but the end result will be identical if you take the projection of R onto xy plane and then you make the dot product. Why? Because B is completely on the xy plane. So in making the dot product, the z component contained in R is not contributing. Right? So it would be identical to say this term RB cosine phi is equivalent to this vector making dot product with this vector. We project this R onto xy plane. How to do that? Multiply by sine theta. Okay? So that's what we have. So we have some way to describe R1. But currently it's in R1 squared, but that's fine. Okay? We can just convert, right? We can just take the square root and invert it. Eventually, what we're interested in is 1 over R1. So this is 1 over R1. And if you still remember, I have made an assumption. My observation point is very far away from the magnetic dipole. So basically, this R is much, much greater than B. Okay? So I can drop this term out. I can make further assumptions using binomial approximation. So let me just show you the end result. Okay? A lot of things can be dropped out, but eventually, once you have a magnetic dipole, a current conducting circular loop, your vector potential would point in the phi direction, and with the magnitude of mu0, the vacuum permeability, multiplied by your magnetic moment, and divided by 4 pi r squared. So another way to write it is, well, to truthfully reveal the magnitude and direction, the quantity is equal to your magnetic dipole moment making a cross product with the AR vector and divided by 4 pi r squared. This form might seem unfamiliar to you right now, but later I'm going to show you a direct one-to-one comparison of the magnetic part to the electrical dipoles, right? But now, if we have A, we can find B, right? All we have to do is perform the curl operation. Of course, we don't like curl, and especially now we're working in spherical coordinate. Now, if you still remember the proper formulation for curl in spherical coordinate system, it's shown here. Okay, no worries. And we're lucky because we only have the A phi component. We don't have A theta component. We don't have AR component. We only have one single component. Okay? Very complicated calculation, but if you still remember this result, this is quite familiar to you. Now, if you still remember electric dipoles, well, examination is coming next Monday. Something AR direction 2 cosine theta, A theta direction sine theta. This should ring some bell. I mean, you should still remember this. Okay. So in the end, I'm trying to show you a direct side-by-side comparison. This is the magnetic vector potential, A. If you compare to the electric potential, V, they are very similar, right? For electric dipoles, here I have 4 pi r squared. For A vector, I also have 4 pi r squared. The only difference is now I have 1 over epsilon 0, and now I have mu 0. Okay? So the end story is, if you understand one particular area very well, all you have to do is replace P by N, 1 over epsilon 0 by mu 0, and dot to cross. Look at it. P, if I change this one to N, right, I make the dot product to cross. 1 over epsilon 0 to mu 0, they are identical. So these are the potentials. The magnetic potential, electric potential, you have to do this conversion. But if you look at the B field and E fields, again, you replace P by N, 1 over epsilon by mu 0, everything is identical. So what does that mean? It means, well, in the far field, remember, all of our derivations for electrical dipole and magnetic dipole are assuming we are very far distanced from the dipoles. And that's the definition of far field. We're very far away. So if I don't really tell you which dipole you're looking at, from the far field, looking far away, I mean, can you tell which is which? They are identical. The field lines of an electric dipole and a magnetic dipole are identical. They're indistinguishable. You can only know which one is which by going into the near field when you walk very close to the dipole. So your distance is very close, which means you move this to gray areas. If you move into the near field, you would see, wow, they are so different. This one is having self-closed loop of field lines, but this one is having connected radiant field lines. So unless you go into the near field and where you can look and examine them closely, otherwise in the far field, you don't feel any difference. So this one, tell yourselves, this one is the resulting field pattern for an electric dipole, right? Positive charge, negative charge, so therefore your field starts from the positive charge and ends at the negative charge. So the fields are actually radiant. But for here, you have the current loop. I'm looking at the cross-section. So all the resulting magnetic field lines form closed loops around the current. Okay? So indeed, even though their construction might be very different, the near field patterns are very distinct, but in the far field, you cannot distinguish one from the other. Right? So for that, I'm going to conclude the first part of magnetic field. Next Monday, you're going to enjoy your examination. So next Wednesday, we're moving to magnetic fields with materials. Are there questions from the students? All right, so good luck next Monday.